With this video, I want to explain some more about the lactate threshold and possible causes of the lactate threshold. And this graph that you've seen before is blood lactate versus treadmill speed or exercise intensity. And so what is causing this lactate threshold? And this list of possible causes of the lactate threshold. And first on the list is low muscle oxygen as a possible mechanism or possible cause. And this now has probably been refuted that it's not one of the major causes, or at least in terms of exercise condition, not a cause of this lactate threshold. This next graph is from some older data, and it looks at lactate concentration on the y-axis over exercise time, and it's a constant steady-state exercise at 70%. Yet here, the blood lactate concentration is decreasing. And if this steady-state exercise, one would predict that the oxygen availability at the muscle cell would be constant. And if it was constant, therefore, if lactate production or concentration was a function of oxygen, if oxygen is constant, then why is this blood lactate concentration decreasing? So this is some evidence that it's not necessarily due to oxygen content. And this is oxygen content at the level of the muscle cell or mitochondria, so muscle hypoxia. This next graph is from some much earlier work, but it's similar. And here it's lactate concentration over time, and it's during prolonged exercise. And certainly the higher intensity of exercises, like 220 watts or 210 watts on the right-hand side, these blood lactates are increasing. Yet with steady-state exercise, as we mentioned earlier, it's either the blood lactates are steady or the blood lactates are dropping with lower intensity exercise. So if at those given exercise intensities, why then is blood lactate changing? Because you would predict there would be no change, at least at a steady state of exercise, there would be no change in oxygen content. So additional evidence that it's not oxygen, or at least muscle hypoxia. So let me review some earlier work or earlier information on the partial pressure of oxygen. We've seen this before, and then let's look at mitochondrial partial pressure of oxygen. So just as a review, the partial pressure of oxygen is equal to the percentage concentration of oxygen, in this case, times the total pressure of the gas mixture. So if we're looking at the partial pressure of O2, in room air at sea level, the total air pressure is 760 millimeters of mercury. The percentage concentration of oxygen is 0.2093. So the partial pressure of O2 would be 159 millimeters of mercury. And it decreases. So it goes from a higher to lower partial pressure of oxygen. So here's ambient air in the trachea, in the alveoli, so it decreases. Another law that will help in terms of gas movement in air is Henry's law, and the amount of gas dissolved in a fluid depends on the partial pressure difference between the gas above the fluid and dissolved in it. And so things want to go from high to low partial pressure of oxygen. And this can be seen by this next figure, that if we start off with a PO2 in room air of 159 millimeters of mercury, here are some numbers we saw before of 149, and maybe arterial blood is about 100. And it's been estimated that at the level of the tissues, the muscle tissue, the partial pressure of oxygen is about 40, and that would probably be more of a resting condition. And this next graph looks at the partial pressure cascade. So here's again room air of 159 and the alveoli, arterial blood of about 100. At the level of the capillaries, maybe 40-ish, and the resting condition, the muscle cells may be 40-ish. And it's been estimated, and there's some measurements, it's difficult to take, but some measurements of myoglobin being at the level of 2 or 3 millimeters of mercury, and mitochondria about 1-ish millimeters of mercury. So these next two graphs are looking at the partial pressure of oxygen in the mitochondria. So let's look at this graph first on the left. So here's relative mitochondrial oxygen uptake as a percent. So think of this sort of as like oxygen consumption maybe at the level of mitochondria. And here's the partial pressure of oxygen, and torr is the same as millimeters of mercury. And so the mitochondrial uptake of the mitochondrial oxygen consumption is maintained till a critical PO2 of about 1 millimeter of mercury, or 1 torr. And then there's this big decrease in mitochondrial oxygen consumption. So if indeed muscle hypoxia was occurring, it would seem to occur at about this critical PO2 value of 1 torr. And then also in 1998 by Richardson, they have two lines or graphs going on here. On the left-hand side is the net muscle lactate efflux. So how much lactate is leaving the muscle cell. And that is this solid line. That's the dashed line. The solid line is intracellular PO2 in torr or millimeters of mercury. And that is the solid line. So in a resting condition, it's high levels of oxygen concentration or high levels of PO2. And as exercise intensity increases, that's going to fall. But notice even at like VO2 max, at 100% exercise intensity, the intracellular PO2 is just under 4. And it's actually maintained at that value of 4-ish from 50% to 100%. So what's happening to blood lactate? Blood lactate in a resting condition at easy exercise is low, but then as we've seen before, there's this classic blood lactate curve where it goes up. This actually is millimoles per minute, so it's a rate of blood lactate leaving the muscle cell. So it goes way up or increases at high exercise intensities, but the PO2 is still maintained at this value of just under 4 millimeters of mercury, just under 4 torr. So it looks like a cause that hypoxia, that low tissue PO2, is not a cause for for the increase in increase in blood lactate concentration. This graph shows active muscle fibers as a percent and exercise intensity. And when I copied the graph, sort of some funny thing happened here with squares. Those are percents. And it's looking at different muscle fibers that are being recruited. So at easy exercise intensities, type 1 fibers are recruited. And those are slow oxidative fibers. They're very oxidative. Then type 2A fibers that are sort of oxidative and glycolytic, intermediate fibers. They're still type 2. They're still fast contracting, but type 2A fibers. And then at a higher exercise intensity, the workload is so hard that all muscle fibers need to be recruited. And these additional muscle fibers that are recruited are type 2X, the fastest contracting, most glycolytic. So they're doing glycolysis. They're doing fast glycolysis. So an end product of fast glycolysis is lactate. So this is not using oxygen as an explanation of blood lactate. It's using muscle fiber recruitment. So the lactate appearance exceeds lactate removal. And this is evidence that it's not muscle hypoxia, that it's the kind of muscle fiber. And these fast twitch muscle fibers have a lactate dehydrogenase enzyme that produces lactate, where the slow twitch fibers have a lactate dehydrogenase enzyme that will produce pyruvates and not lactates. The higher exercise intensity, the more epinephrine is released. And so these are explanations for the increase in the rate of lactate appearance. So more epinephrine, greater fast twitch muscle fibers, and as I mentioned, the type of the lactate dehydrogenase enzyme. So LDH, or lactate dehydrogenase, is found in a variety of tissues, and it has different isoforms. So an isoform is a very similar enzyme, yet a slightly different protein. And LDH's role is the interconversion of pyruvate to lactate and lactate to pyruvate. So this is just looking at pyruvate to lactate. They're both 3-carbon molecules, and NADH and NAD that is required for that reaction to go. And LDH would also catalyze the reaction going in the opposite direction. So there are different isoforms of this enzyme. An isoform is the same name, but just different, actually, subunits. And the subunits are abbreviated H for heart and M for muscle. And these subunits get together to form 5 different isoforms of LDH. And LDH1 is the isoform of the enzyme that contains all the heart, that's where it was first discovered, and the heart isoforms. And this is found in heart tissue and oxidative muscle tissue. And you can look and see at the different combination of these isoforms. LDH5 has all muscle subunits, and this is found in fast twitch striated muscle. So the type 2X muscle that are the fastest contracting muscle, they would have this LDH5 isoform that is producing lactate. So the type of LDH isoform is the enzyme that converts pyruvate to lactate or lactate to pyruvate. LDH muscle, that form favors the formation of lactate, lactic acid. The LDH heart, which is found in type 1 muscle fiber, favors lactate to pyruvate. And in a very simple diagram, this would be in the cytosol of the cell. We're breaking down glucose to actually 2 molecules pyruvate. This is inside the middle part of this graph is my diagram is inside the mitochondria and acetyl-CoA and the Krebs cycle. And lactate, then, if it is changed into pyruvate, that's LDH heart enzyme, or LDH1, or has all the heart subunits. LDH5, or has all the LDH muscle subunits, would catalyze pyruvate to lactate. Great. So that is lactate appearance. In addition, lactate appearance is a function of epinephrine concentration or epinephrine release. An epinephrine or adrenaline, it can activate glycogenolysis, so it breaks down glycogen more quickly. It activates glycolysis, so it will increase the rate of glycolysis. And it also inhibits fat oxidation, so it inhibits lipolysis. So these first 2 on the list would increase the rate of fast anaerobic glycolysis. So automatically more lactate is being produced. And that can be shown on this next graph. Here's blood lactate concentration on the left-hand side y-axis in millimoles. And on the right-hand side y-axis is epinephrine concentration, nanograms per mil. And the graphs are identical, and they also have this same sort of exponential relationship. And wherever it's 60 or 70%, there's sort of a reflection point where there's a big increase in epinephrine and a big increase in lactate. This can also be shown, and we've mentioned this before, with McArdle's patients and with glycogen depletion. Both of these are examples of slowing down the rate of glycolysis. So McArdle's patients, it's a rare genetic disorder, and it inhibits the phosphorylase enzyme that is required for glycogen breakdown. And these McArdle's patients along with glycogen depletion experiments, show no lactate threshold during exercise. So slowing down the rate of glycolysis or the rate of glycogenolysis equals no lactate threshold point.